In the year 2087, Dr. Elena Vasquez stands alone in the observation deck of the Kepler Deep Space Observatory, floating silently in the outer reaches of our solar system. Through the massive viewing port, she gazes upon a sight that would have been impossible to witness from Earth. The Andromeda Galaxy, now close enough to fill nearly half the sky, its spiral arms twisted and distorted by the inexorable pull of gravity. The Great Collision has begun. What started as two separate island universes 4.5 billion years ago is now becoming one cosmic metropolis of stars, gas, and dark matter. But as Elena watches this celestial dance unfold through time-lapse imagery spanning millions of years, she notices something troubling. The new stars being born from this galactic merger burn with a different light than those of the past, dimmer, redder, shorter-lived. They are the last gasps of stellar formation in a universe that is slowly, but inevitably, running out of the raw materials needed to create new suns. This moment of cosmic transition forces us to confront one of the most profound questions about our universe. When did the cosmos stop creating its most magnificent titans? Why are the giant stars, quasars, and massive structures we observe today merely echoes of a more violent and creative past? To understand our place in this cosmic timeline, we must journey back to the very beginning, to an epoch when the universe was radically different from the one we observe today. 13.8 billion years ago, in the first moments after the Big Bang, the cosmos was a seething cauldron of pure energy, so hot and dense that not even atoms could exist. Matter and antimatter annihilated each other in spectacular bursts of gamma radiation, while fundamental forces that today seem completely separate, electromagnetism and the weak nuclear force, were unified into a single, primordial interaction. As the universe expanded and cooled, it passed through a series of phase transitions that would determine everything about the cosmos we inhabit today. First came the era of nucleosynthesis, lasting only 20 minutes, during which the first atomic nuclei of hydrogen and helium were forged in the cosmic furnace. Then followed the longest night in cosmic history, nearly 400 million years of darkness, when no stars existed and the universe was filled only with primordial gas clouds, slowly condensing under their own gravity. But when the first stars finally ignited, they were monsters beyond anything we see in today's universe. These population 3 stars, as astronomers call them, were titans that could reach masses of 300 times our sun or more. They burned with the fury of cosmic forges, their cores reaching temperatures so extreme that they could fuse elements all the way up to iron in their nuclear furnaces. Unlike the long-lived red dwarfs that populate our modern galaxy, these giants lived fast and died spectacular deaths, exploding as hypernova that could be seen across the entire observable universe. The death of these primordial giants was not just the end of individual stars. It was the beginning of cosmic enrichment. Every heavy element in your body, from the calcium in your bones to the iron in your blood, was forged in the nuclear furnaces of these ancient behemoths. When they exploded, they seeded the pristine hydrogen and helium of the early universe with the first metals, creating the chemical diversity that would eventually allow planets, and life itself, to form. It was around this time, roughly 11 billion years ago, that another class of cosmic titans reached their peak, the quasars. These supermassive black holes, often weighing billions of times more than our sun, consumed matter at such prodigious rates that they outshone entire galaxies. The brightest quasars of this era radiated with the power of trillions of stars, their accretion disks glowing white-hot as material spiraled inexorably toward the event horizon. Dr. Martin Schmidt's discovery of the first quasar in 1963 revolutionized our understanding of the early universe. What initially appeared to be a nearby star turned out to be a galaxy-sized beacon, from when the cosmos was only a quarter of its current age. As more quasars were discovered and mapped, a startling pattern emerged. The most powerful ones all existed in the distant past. Today's universe, it seemed, no longer had the conditions necessary to create these cosmic lighthouses. The reason lies in what cosmologists call the cosmic downsizing phenomenon. In the early universe, galaxies were smaller but much more active, with dense concentrations of gas that could feed supermassive black holes at tremendous rates. As the universe expanded and evolved, these gas reservoirs were gradually consumed or blown away by stellar winds and black hole feedback. The cosmic web itself, that vast network of dark matter filaments that connects all large-scale structures, became increasingly sparse and stretched, making it harder for galaxies to accrete new material. This transformation wasn't just about individual objects becoming smaller or dimmer. The entire character of cosmic evolution was changing. The universe was transitioning from an era dominated by violent, rapid growth to one characterized by gradual decline and exhaustion. Computer simulations run by teams at institutions like the Max Planck Institute for Astrophysics show this transition in stunning detail. In their models, the early universe resembles a cosmic construction site, galaxies growing rapidly through mergers, stars forming at breakneck pace, and supermassive black holes swelling to enormous sizes as they feast on abundant gas. Fast forward to today, and those same simulations reveal a very different cosmos. Star formation rates have declined by more than an order of magnitude since their peak 10 billion years ago. The most massive stars that form today rarely exceed 50 solar masses, a far cry from the 300 solar mass titans of the early universe. Even the supermassive black holes at the centers of galaxies have entered a period of relative dormancy, with only occasional flare-ups when an unlucky star wanders too close to the event horizon. The Hubble Space Telescope's deep field observations provided some of the most compelling evidence for this cosmic transformation. By looking at galaxies at different distances, and therefore different times in cosmic history, astronomers could create a time-lapse movie of universal evolution. The most distant galaxies, seen as they were over 10 billion years ago, appear chaotic and irregular, often in the process of violent mergers that trigger massive bursts of star formation. Closer galaxies, representing more recent cosmic epochs, show the orderly spiral and elliptical structures we're familiar with today. But perhaps nowhere is this cosmic decline more evident than in the fate of galaxy clusters themselves. These vast gravitationally bound systems, containing thousands of individual galaxies, represent the largest structures in the universe. In the early cosmos, clusters were still actively forming through the merger of smaller galaxy groups. Today, while some clusters continue to grow through the accretion of smaller systems, the overall rate of cluster formation has slowed dramatically. The Atacama Large Millimeter Array, scanning the southern skies from its high-altitude perch in the Chilean desert, has captured this transition in exquisite detail. Its observations of distant galaxy clusters reveal a cosmos in the throes of active construction, with galaxies still actively forming stars at rates hundreds of times higher than anything we see locally. These ancient galaxy clusters are like cosmic nurseries, churning out new generations of stars and planetary systems at a pace that seems almost frantic compared to the sedate evolution we observe in our cosmic neighborhood. Yet even as we document this decline, we're simultaneously witnessing the universe's final creative acts. The James Webb Space Telescope, with its unprecedented infrared vision, has peered deeper into cosmic history than ever before, revealing galaxies that formed when the universe was barely 500 million years old. These primordial systems are the last gasps of the universe's most creative epoch, island universes caught in the act of rapid assembly during the final moments of cosmic youth. What makes this decline particularly poignant is its apparent inevitability. Unlike biological evolution, which can produce increasing complexity over time, cosmic evolution seems to follow a more thermodynamic trajectory, from order to disorder, from concentration to dispersion, from brightness to darkness. The universe's expansion, driven by the mysterious dark energy that comprises 70% of all cosmic content, ensures that galaxies will become increasingly isolated over time. Dark energy itself represents perhaps the most profound mystery in this cosmic narrative. Discovered through observations of distant supernovae in the late 1990s, dark energy appears to be accelerating the expansion of space itself. As galaxies drift apart from one another, the raw materials for future star formation become increasingly difficult to gather. Gas clouds that might once have collapsed to form new stellar nurseries are instead stretched thin by the expanding fabric of spacetime. The consequences of this accelerated expansion extend far beyond simple cosmic loneliness. Computer models suggest that in roughly 100 billion years, all galaxies beyond our local group will have receded beyond the cosmic horizon, their light redshifted into invisibility. Future civilizations, should any exist, will inhabit a universe that appears to contain only their own galaxy and its immediate neighbors. The vast cosmic web that we observe today, that magnificent network of galaxy clusters, filaments, and voids that gives large-scale structure to the universe, will have faded into invisibility. But the decline doesn't stop there. Even within our own local group of galaxies, the cosmic titans are facing extinction. The Milky Way's supermassive black hole, Sagittarius A star, once likely rivaled the great quasars of the early universe in brightness. Today it slumbers quietly at our galaxy's center, consuming matter at such a modest rate that it barely glows in radio waves. Occasionally it flickers to life when a gas cloud or unlucky star strays too close. But these outbursts are pale shadows of the cosmic beacons that once illuminated the early universe. The Event Horizon Telescope's historic image of the supermassive black hole in galaxy MADI 7 provided a window into this cosmic twilight. While the black hole itself remains hidden behind its event horizon, the glowing accretion disk around it tells the story of a once mighty quasar now reduced to a relative whisper. The material spiraling into MADI 7's central black hole glows at only a fraction of the luminosity that characterized similar objects in the early universe. Even the stars themselves are changing. The giant molecular clouds that serve as stellar nurseries are gradually being disrupted by the accumulated effects of stellar winds, supernova explosions, and cosmic ray bombardment. The most massive stars, those cosmic forges capable of producing elements heavier than iron, are becoming increasingly rare. Future generations of stars will be smaller, longer-lived, but less capable of the nuclear alchemy that enriched the universe with heavy elements. This stellar evolution has profound implications for the possibility of life in the far future. While red dwarf stars can burn for trillions of years, their planetary systems receive less energy and may be tidally locked, with one hemisphere permanently facing the star while the other remains in eternal darkness. The comfortable, stable conditions that allowed life to evolve on Earth may become increasingly rare as the universe ages. Yet there's a strange beauty in this cosmic decline. The same processes that are bringing the age of giants to a close are also creating some of the most spectacular phenomena we observe today. When massive stars can no longer sustain nuclear fusion in their cores, they collapse catastrophically, creating neutron stars and black holes. The collision of these ultradense objects generates gravitational waves, ripples in spacetime itself, that carry information about some of the most violent events in cosmic history. The Laser Interferometer Gravitational Wave Observatory has opened an entirely new window into these cosmic death throes. Each gravitational wave detection represents the final moments of stellar titans, neutron stars spiraling into each other with such violence that they briefly outshine entire galaxies in gravitational radiation. These collisions also serve as cosmic foundries, creating elements like gold and platinum through rapid neutron capture processes that cannot occur in any other astrophysical environment. As we stand at this cosmic crossroads between the age of giants and the era of decline, we're forced to confront our own place in the universe's timeline. The elements in our bodies were forged in the nuclear furnaces of massive stars that lived and died billions of years ago. The gold in our jewelry was created in neutron star collisions that sent shockwaves across spacetime. We are, quite literally, the universe becoming aware of itself, a collection of ancient stardust organized into consciousness, just in time to witness the cosmos entering its twilight years. The realization that we may be living through the universe's final golden age adds a layer of urgency to our cosmic observations. Every distant galaxy we observe, every quasar we detect, every supernova we catalog represents a glimpse into a more dynamic and creative past that can never be repeated. The universe is not just expanding. It's diluting, cooling and gradually exhausting the processes that created the rich tapestry of structures we see today. Future space telescopes, like the proposed Lynx X-ray Observatory and the extremely large telescopes being built in Chile and Hawaii, will push even deeper into cosmic history, potentially observing the very last generation of population 3 stars. These observations may reveal the exact moment when the universe transitioned from its age of titans to the more modest era we inhabit today. But perhaps the most profound implication of cosmic decline is what it tells us about the nature of existence itself. In a universe governed by entropy, where energy gradually disperses and structures slowly decay, the temporary concentrations of matter and energy that we call galaxies, stars, and planets represent brief victories against the cosmic tide. Life, with its ability to create local order from universal chaos, may represent the ultimate expression of this anti-entropic tendency. As the universe continues to expand and cool, as the last giant stars exhaust their nuclear fuel and the final quasars fade into darkness, the cosmos will enter what cosmologists call the degenerate era. In this far future, roughly 10 to the 37 years from now, even protons may decay, leaving behind a universe populated only by electrons, positrons, and photons, the fundamental particles slowly cooling toward absolute zero. Yet even in this seemingly bleak future, the universe may harbor surprises. Quantum mechanics suggests that given enough time, random fluctuations in the vacuum of space could spontaneously create new structures, new galaxies, perhaps even new forms of life. The timeframes involved boggle the human imagination, periods so vast that the entire history of our universe from Big Bang to present would represent merely the first tick of a cosmic clock. Standing once again with Dr. Vasquez in that observation deck in 2087, watching the collision of our galaxy with Andromeda, we're witnessing both an ending and a beginning. The merger will trigger one final burst of star formation as gas clouds collide and compress, creating new stellar nurseries from the disrupted material of 2 ancient galaxies. But this burst of activity will consume much of the remaining gas, leaving the merged galaxy, which astronomers have already nicknamed Milkomeda, with fewer raw materials for future stellar generations. In the collision's aftermath, the night sky will be transformed. New constellations will form as stars are flung into different orbits by the gravitational chaos of merger. Some star systems will be ejected entirely, becoming lonely wanderers in the vast spaces between galaxies. Others will be drawn closer together, creating dense stellar neighborhoods where planets might enjoy the light of multiple suns. The supermassive black holes at the centers of both galaxies will eventually merge as well, creating a single, even more massive object at the heart of Milkomeda. This final coalescence will generate gravitational waves powerful enough to be detected by advanced civilizations billions of light-years away, assuming any still exist to observe them. The merged black hole will likely remain dormant, occasionally flaring to life when a star strays too close, but never again matching the sustained brilliance of the quasars that once illuminated the young universe. As we contemplate this cosmic future, we're reminded that every moment of existence, every sunrise, every flower that blooms, every child that laughs occurs against the backdrop of universal impermanence. The atoms in our bodies will outlast our planet, our star, and our galaxy, but they too will eventually decay, returning their energy to the void from which they came. In this context, consciousness itself becomes something precious beyond measure, the universe's brief attempt to understand its own nature before the lights go out forever. The giants of the early universe, those massive stars, brilliant quasars, and rapidly growing galaxies, were cosmic pioneers, exploring the full range of possibilities that physics allows. Their legacy lives on in the heavy elements they created, the black holes they left behind, and the inspiration they provide to those of us fortunate enough to observe their ancient light. We may live in an era of cosmic decline, but we also live in an age of cosmic understanding, when for the first time in universal history, matter has organized itself into forms capable of comprehending the very cosmos from which it emerged. In the end, the question of when the universe stopped making giants may be less important than recognizing that we ourselves are giants in our own right, not in mass or luminosity, but in our capacity to observe, understand, and find meaning in the vast cosmic drama unfolding around us. We are the universe's way of bearing witness to its own magnificent, temporary, and ultimately poignant journey from simplicity to complexity and back again. In our brief moment of consciousness, we carry the light of understanding into a cosmos that is slowly, but inevitably, returning to darkness.